Okay. All right. Welcome everyone to the second week of our workshop, matrix workshop, and today we are happy to have GaYee Park from University of Massachusetts Amherst, who will be talking about Naruse hook length formula for skew-shaped tableau. Go ahead. Welcome, GaYee.
Thank you for the introduction, and thank you for the organizers as well. It's not working. Okay, so here is the overview of the talk today. I will be going over some background information, including hook length formula and the Naruse hook length formula, and talk about their Q analog, and also talk about posets and its linear extensions, and introduce you to a new family of posets called mobile posets and my results on it. And we'll be talking about brief method of proof, and if we have time, I'll be talking about the case of inversion index. So let's start with Young diagram. Given a partition of any number, we can represent it as a Young diagram. So here we have a partition of 7 in two different ways, 3, 2, 2, and 2, 2, 2, 1. And I have their Young diagram in English notation. And given the diagram, hook of the cell is all the cells below and all the cells to the right and the cell itself. So this is the hook of this blue cell over here. And the hook length is given as this formula where lambda sub I minus I is the cells on the right, and the lambda prime sub j minus j is the cells on the bottom, and plus 1 is the element itself. And given the diagrams, we can now fill it with numbers from 1 through n so that it is increasing in rows and columns. And we call this standard Young tableau. So for the shape 2, 2, 2, 1, we have this example of standard Young tableau, and you can see that this is not the only way of filling this diagram into this tableaus, because I have another one written here. And the question is, given a fixed shape, how many standard Young tableaus are there for that particular shape? And in general, counting number of standard Young tableau is interesting, and one motivation is that it gives a dimension of irreducible representation of symmetric group Sn. In this example of S3, there are 3 irreducible representations, and the fact that this 2, 1 partition have 2 different ways of filling this into a standard Young tableau corresponds with the dimension of standard representation is 2 for S3. And to count this, we have the famous hook length formula by Frame, Robinson, and Thrall, given as a product over 1 over the hook length of all the elements in the diagram. So back to our example, in blue, I have the hook length of each of the elements, and if I plug in all these numbers into the formula, we have 14 standard Young tableaus. So let's move on to now Naruse hook length formula. We can generalize this further into skew shapes by taking a subset mu of lambda and coloring in the corner of lambda by this mu. And so here we have 3 different examples of these skew shapes, and later we'll be talking about a particular skew shape tableau called border strip. So the definition is that it's connected skew shape without any 2 by 2 squares. So this one has a 2 by 2 square, so it's not a border strip. This one is disconnected, so it's not a border strip. So this one is a border strip, and visually you can literally think of it as a ribbon strip of width 1. And again, you can fill these skewed diagrams in with numbers from 1 through n and make them into tableau as well, increasing in rows and columns, and here are the examples. And let's focus on this border strip here on the right. And here I have written all the standard Young tableau of this particular skew shape. And you can see that this inner corner here has a little bit more degree of freedom than for the case of straight shape, because it is no longer restricted by the elements above. So this can be as small as 1 if it really wanted to. So that adds a little bit of a complexity to these skew shape tableaus. And there's no known hook length formula, at least in product form, to count the number of standard Young tableau for skew shapes. until Naruse came up with a new type of hook length formula called Naruse hook length formula, where it's almost like a original hook length formula. So we're still producting. We are still we have a product over 1 over the hook length of all the elements, but we are also summing over these objects called excited diagrams, which I will define in the next slide. So thanks. Originally, the formula was proven quite algebraically, but the combinatorial proof was shown by Morales, Park, and Panova based for the case of border strip, which I defined before. So these excited diagrams are obtained by this thing called excited moves. Whenever you see this pattern 2 by 2, where this corner is colored in like this, you can shift this colored corner diagonally down like that and obtain another excited diagram. For this example, we see the pattern over here. So we can slide this colored corner down diagonally to here, and this is our next excited diagram. That opens up this box. So we have another pattern here. So we can slide this corner down diagonally, and we have another excited diagram. And this move terminates because these colored corners can't go anywhere else. This tells us that there are 3 excited diagrams for this particular skew shape. So let's plug it into our formula. This, again, I have in blue written down the hook length of each of the elements. And the formula was sum over all the excited diagrams. So each of this fraction corresponds to each of the excited diagrams. So this one corresponds to this one, and that one. Plugging in all the numbers, we indeed have 9 standard Young tableaux for this particular skew shape. Now let's raise the situation up to Q analog. In the case of Q analog, we are now working with semi-standard Young tableau, which is the tableaus where we're still increasing strictly in column, but weakly in rows. So we get to now repeat numbers and also insert 0. Short function of x of i's is defined as a sum over the semi-standard Young tableaus. So to the left, we have the original standard Young tableau, and here now we have the semi-standard Young tableau. There are 2 zeros and 2 ones, weakly increasing in rows and strictly increasing in columns, and this can be represented as x of 0 to the power of 2, because there are 2 zeros, x of 1 to the power of 2, and I'm missing a bunch of semi-standard Young tableau here, but if I were to write everything and represent all of them into these variables, then I would indeed have the short function. If I replace all the x of i's with q to the power of i's, then I would have a q analog of short function, where the powers of q is the sum of all the insertions in the tableau. So this would be q to the power of 2, q to the power of 4, these two would be q to the power of 10. And this is true for both straight and skew shape. And they also have the product formula. So this is a product formula by Stanley, and if you take q is equal to 1, then you would also have the original hook length formula back. And Morales, Park, and Panova also came up with q analog for Naruse hook length formula as well. We are still summing over the excited diagrams, and we have these extra accessories, q to the power of sum of hook lengths of supports of broken diagonals, which I will also define in the next slide. The broken diagonals are also obtained from excited moves. So whenever you are performing an excited move and sliding this colored box down, you're also shifting this diagonal to the left. So these diagonals come originally, if it's a straight shape, from all the diagonals below the main diagonals. And when you're making them into a skew shape, these diagonals get pushed by all the mu's. So these are the original diagonals. And if we were to perform this excited move onto, let's say, this corner here and moving this blue box down diagonally, then this blue diagonal would be broken into 2 pieces by shifting the segment of blue diagonal to the left according to this move. So back to our example, for these three excited diagrams for this particular skew shape, in red are the spots for the supports of the broken diagonals, and they would be counted into the formula for the Q analog of Naruse-Hoekling formula. Okay, so now let's move on to posets. Given a poset, a partially ordered set, the linear extension of it is an ordering of all the elements so that it's compatible with the ordering of the poset itself. So here we have a poset A, B, C, D, and B and C are incomparable. So B and it doesn't matter whether B comes before C or C comes before B, as long as they're both after A and before D. So we have two linear extensions, A, B, C, D, and A, C, B, D. And the number of linear extension is denoted as E of P, and there are two of them. And in general, computing this number of linear extension is hard, and I think the technical term is sharp P hard, shown by Brightwell and Winkler. So why am I talking about poset all of a sudden? Take this poset A, B, C, D, and rotate it 90 degrees to the right, then I have a Young diagram again. And take these linear extensions, A, B, C, D, and A, C, B, D, and take each of the positions of A, B, C, D, and then insert it into these boxes, then I have again the standard Young tableau. So the very fact that the insertions of B and C must be greater than A, but less than D in the terms of standard Young tableau is equivalent to the fact that element B and C must come after A and before D in terms of linear extensions in the posets. And this is true for general case for both skewed and straight shape. The number of linear extensions of posets derived from a Young diagram is equivalent to the number of standard Young tableau of that particular shape. We can also take this to Q analog as well. In Q analog, we're dealing with labeled posets. We're labeling the poset with numbers so that the linear extensions would give a sequence of number, and we get to analyze that sequence. The two most popular, I would say, types of Q analogs of number linear extension is major and inversion index. Where the major index is defined as the sums of all the positions of the descent, where it's defined here. Descent is where is the position of number, and the number that comes right after is less than the number itself. I'll do examples. And also for inversion case, we're looking at the inversion index of the sequences of linear extensions, where inversion is the number of positions where the number coming after are less than the number itself. I'll do examples. So here we have the poset ABCD and its linear extensions. Let's label this 1, 2, 3, 4. Then the linear extension is now 2, 1, 4, 3 and 2, 4, 1, 3. And we'll look at the major and the inversion index of the sequence. For major index of 2, 1, 4, 3, there is a descent going from 2 to 1 in position 1, and there's a descent going from 4 to 3 in position 3. So the major index for this one is 1 plus 3 is equal to 4. For the case of the sequence 2, 4, 1, 3, there is a descent from 4 to 1, which is in position 2, and that's it. So the final EQ mod for this poset with this particular labeling would be q to the power of 4 plus q to the power of 2. And for the inversion case, there's an inversion from 2 to 1 and 4 to 3, so there are a total of 2 inversion. And for the 2, 4, 1, 3, 2 to 1 for inversion doesn't have to be right after. So 2 to 1 is an inversion. 4 to 1 and 4 to 3 is another 2 inversions. So we have a total of 3 inversions. So the equation would be q to the power of 2 plus q to the power of 3. So if I label these posets in a very particular way, I can again relate this to the tableaus that I worked with before. So for the EQ mod of a very particular labeling called sure labeling, there is also a product formula for this. So now this is to show the relationship between the sure function and the EQ mod of the posets coming from this particular shape of Young diagram. And this is also true for skew shape as well. So basically, this is to show that the posets derived from Young diagrams can be related to tableaus by having these product formulas. But we can do even better. There's a large family of posets called decomplete posets that includes, but not limited to, the posets arised from Young diagrams. They also include the rooted trees and shifted Young diagrams. And one of the reasons to group them into such a large family is that they behave very nicely in a sense that they all have this product formula to count the number of linear extensions. They also have it for the major index. So here we have the product formula for the major index for any labeling of the poset. And also for the inversion index as well, with a couple of conditions. First of all, note that this is not for any complete poset. This is only for rooted tree posets, and with a very particular type of labeling called natural labeling. Natural labeling of a poset is if x is greater than y in the poset, then the labeling of x must be greater than the labeling of y. That's natural labeling. So for the inversion case, there's all these conditions, but for the major case, it seems like everything works really well. So the question is, are there other posets with Naruse hook length formula generalizing these formulas for E of P? So on one hand, we have all these decomplete posets with very nice product formulas. On the other hand, we have border strips with Naruse hook length formula. And I know that it's not just border strip, it's for all skew shape, but border strip is the only one that we actually understand the combinatorics of it. And if we combine them together, we have something called mobile posets. I press something and then it moves somewhere, but I think it's okay. All right. Mobile posets were first introduced by Garver, and Mathern and Morales, and it is obtained by hanging the complete posets onto the border strip. So here we have this example of a mobile poset, and as you can see, it resembles this toy mobile here on the right. So we have a mathematical toy mobile. And when they introduce this family of posets, they came up with a determinant formula for the number of linear extensions and also for its Q analog as well. And they asked if there is a Naruse formula for this type of posets. So here is a Naruse hook length formula for mobile posets, where it looks almost like the original Naruse hook length formula, where we're summing it over its excited diagrams with some extra accessories to count in the hook lengths of the decomplete posets. And also we have to redefine the definition of hook now because it's a new type of posets. So the definition of hook for mobile poset is the original hook length plus the extension to its decomplete poset. So all the decomplete poset hanging below and to the right of the element, in particular for this case, this pink region, we are counting those in and we're adding in the sizes of these decomplete posets into the hook length. For this, original hook length was 3, and now I'm adding 4 in, so now the new hook length is 7. We also have it for the major index as well. To compare it with the original one given by Morales, Pack, and Panova, again, we have these extra accessories to count in the hook lengths of the decomplete posets, and the the broken diagonal hook length of the broken diagonal support is also replaced by the definition of new hook length as well. So here's an example. Here is a mobile poset, and again in blue I have the hook length of each of the element, and in red I have this particular labeling that I'm working with, and the number of linear extensions for this poset is 33,000. And if I want interested in the major index of this, then plugging in everything to the formula, we have this very nice polynomial, which is the equimage of this poset. So we have time. Let's move on to the method of proof briefly. The proof itself is not original. We follow the proof for the border strip by Morales, Pack, and Panova. So in their paper, they introduced two lemmas that contains the sum over this map called mu to nu. So let me explain that first. Given a skew-shaped lambda over mu, there are inner corners. For this case, there's this u, and there's another inner corner here, another inner corner here. If you were to rotate this again 90 degrees to the right and view this as a poset, you can view this these inner corners as the maximal elements of this poset. And if we remove one of this inner corner, then because we're working with border strips, we're disconnecting the diagram into two pieces, nu1 and nu2. So the map, such action is denoted by the map mu to nu. And we are summing over all possible removal of the inner corners for this shape. So the first, we have Chevalley formula, which really comes from this multivariate function, which satisfies the Chevalley relationship. So because we know that this function satisfies this relationship, all we need to do is find appropriate xi's and yj's so that xi minus yj would equal to the new hook length definition we have for the mobile poset. And we can rewrite this f in terms of h. Did I say h before? H here is the sum over the excited diagrams on the right-hand side of my formula. So I can rewrite this f in terms of h, and I have now the variation of the Chevalley formula. This f also is an evaluation of short factorial function, which was used to prove the Q analog case by Morales, Pack, and Panova. Unfortunately, I wasn't able to relate anything to the short functions or or the factorial short function because we are working with mobile posets now and not the tableaus or the semi-standard Young tableau, but we were able to show at least this relationship combinatorically. Next, we have this recursion formula. So recall that the action mu to nu is the removal of the maximal element of this poset. And any linear extension of this poset would end with one of the maximal element. So this formula is basically saying that we can categorize all the linear extensions of this poset by its final element. But the poset here on the right is disconnected. And we do have the formula to count the number of disconnected posets even in Q analog in major case. But we have one more problem. So here's an example of a mobile poset, and I am removing the inner corner 12, and I have this disconnected poset here. So now I am trying to count the number of linear extensions on the left-hand side by taking the linear extensions of this disconnected poset and adding 12 at the end, because that would be the linear extension of this poset. In the case of Q is equal to 1 case, that's it. That's very simple. You just add the maximum element at the end, and that's all. But for the case of Q analog, and we're working with, let's say, major index, then if a linear extension of the disconnected poset ends with 13, and if I add 12 at the end, then 13 to 12 would have an extra major index. Whereas if the linear extension ends with 9, and if I add 12 at the end, then 9 to 12 would not give any extra major index. So depending on which element this linear extension ends with, the linear extension of this poset would have either an extra major index or not. So now I have to figure out how to distinguish the linear extensions that ends with nu1 or nu2. So denoting the linear extensions that ends with a particular s as semicolon s, we have this formula that can help us distinguish which of the linear extensions of this disconnected poset would end with either the elements in nu1 or with the elements in nu2. So this formula at the end would help us distinguish that and eventually prove the recursion formula needed to prove the final theorem. So if I have enough time, I would like to talk about the case of the inversion index briefly. So for the case of inversion index, here is a theorem that we have. And let me just, for now, compare it with the case of major index really quickly. And just even out of the blue, you can see that there are some ugly parts in the inversion index. There's this extra plus PD, and there's this extra condition here. This is not for all mobile posets. This is for particular labeled tree posets. So the product formula, recall that when I was talking about the decomplete posets and introduced the Q analogues of those decomplete posets, it only, for the inversion case, it only had the formula for the case of rooted trees. And it was very specific. The labeling of the trees had to be natural. So there's that. And there's even more restrictive labeling rules. So in part of the method of proof, I talked about the fact that we need a formula to count the number of linear extensions for disconnected posets. So here is the formula to count the number of linear extensions for disconnected posets for the case of inversion index. And it looks very much like the major index case, but it has a very, very specific conditions for its label. So whatever the label that my mobile poset has, it must also follow this. So we were able to come up with a particular type of labeling. It must satisfy 3 conditions. The first is that it must satisfy the fact that all the rooted trees are naturally labeled. So here, for example, 9 is greater than 8 or 7, so the label is greater. And it has to satisfy this my short labeling definition. So it must increase as we're going through this border strip. As you can see, 4, 5, 6, 10, 11, 12, it is increasing in this way. And the third condition must follow this very specific conditions for the disconnected poset here. So if I remove any inner corners, then everything to the left is greater than everything to the right. So it has a very, very specific types of labeling conditions that it must follow, but indeed, it would work. So here is an example of the inversion index where red is the labels. The hook length is the same as the blues that I've shown before. And plugging everything in, this would be the inversion index formula, the answer for this particular posets, which one can check on Sage as well. So that is all I have today. So we talked about the hook length formula, and it's Naruse hook length formula, its generalizations into mobile posets, and also talked about the case of inversion index and its restriction. So that is all I have today. Thank you.
Thank you so much. Thank you.